Hello everyone and welcome back. So we are going to continue the discussion that we began in the last time, in the last lesson. We were discussing, if you recall, stress strain behavior of soil and rock. We are going to continue that discussion and we are going to learn more aspects of stress strain behavior of soil and rock in this particular presentation. Now the objectives of this lesson is that after this at the end of this lesson we should be able to estimate the shear strength parameters from triaxial testing. Then we should be able to list the major characteristics of stress strain response of soil and rock. We should be able to calculate effective stress for simple geologic stratigraphy, and finally we should be able to list the major factors that affect the shear strength parameters of soil and rock. Okay, so now we continue with the discussion that we started in the last time. If you recall, we were discussing how to analyze the data obtained from a series of triaxial tests performed on specimens of intact samples of rock or soil samples. Now in the lesson that we had last time, we considered three different triaxial tests on three identical samples of rock or soil performed at three different cell pressures. Now at the end of the lesson I said that what we have to accomplish for obtaining the shear strength parameters is to plot the Morse circles representing the state of stress at failure for each one of those tests. Okay, so that is what we do in this particular slide. So if you recall that the first test of the series of triaxial tests was conducted at the smallest value of cell pressure, and the data obtained from the triaxial test, the deviatoric data, are presented on the plot near the top left of this particular slide, and for this data we have plotted the Morse circle shown at the bottom right. Now what you should notice here is that sigma C1, that is the cell pressure under which this particular test was conducted, is the minor principal stress, and if you add the deviator stress at failure for this particular test, and sigma d, that is given by sigma df1, if you add that one to sigma C1, then you are going to get the major principal stress for this this situation. So the Morse circle for this combination of stress, this state of stress, is plotted on the tau sigma space shown near the bottom right. And now what we are going to do, we are going to plot the corresponding data from the next test, which was conducted at a somewhat higher level of cell pressure, and in this particular test we obtained at failure a deviator stress of sigma df2. So the failure is denoted by subscript f, and the second test is denoted by subscript 2 in this particular case. So here, as we did for the first test, is that the minor principal stress is sigma C2, slightly larger than the previous value. Then we add to that one sigma df2, and that gives us the major principal stress, and we plot the corresponding Morse circle, which is larger than the previous Morse circle. Okay, then we do the same thing for the third test, and we get a third Morse circle, a part of which is only shown on this particular plot, and here the minor principal stress, like the previous cases, is sigma C3, and the major principal stress is sigma C3 and sigma DF3. So, all these tests you recall were conducted without considering pore water pressure, and they were conducted in a very slow rate, so that there was no chance actually for the pore water pressure to develop. What we mean by pore water pressure will have to be discussed as the time comes. And the other thing is, if the test were to be conducted on dry samples, you would get the same kind of stress strain plots and same sort of Morse circles. So repeating what we said is that the Morse circles corresponding to the 3 triaxial tests are shown on the tau sigma space at the right of this particular screen, and now our attempt is to find out what are the strength parameters. You should also notice there is an orange line that actually is tangential to the 3 Morse circles, and that is normally the case. If you conduct a series of triaxial tests, then if you construct the Morse circles at failure, then more often than not what happens, you could actually connect them with a common tangent as shown by the orange line plotted on the tau sigma space on this on the screen there. Now, the characteristics of the orange line are the strength parameters that define the ultimate strength of this of the rock or soil samples which were tested in this series of triaxial tests. What are the characteristics? Since it is a linear linear line, it is a straight line. The common tangent to the 3 Morse circles is a straight line. So the characteristics are really the angle which the line makes with the sigma axis and the intercept that the line has at sigma equal to 0 axis, tau axis. So these two parameters are also indicated on this on your screen there. So the angle here is denoted by symbol phi, and the intercept is denoted by using symbol c. So the angle phi is called angle of internal friction, and this quantity c, which is measured in units of stress, is called cohesion intercept. So this c and phi essentially are the shear strength parameters that are of general interest in such problems. Now you should notice that here we are saying that the failure envelope indicated by the orange line is a straight line, but in many cases the envelope is slightly curved and it is actually convex. It is convex upward. So if you have got to consider such type of material, then a linear failure envelope may not be appropriate for your problems. Now what we want to do in this case is to simplify. Here we made a simplifying assumption that at least for the range of stresses that is considered in this particular problem, namely between here and here, the failure envelope can be approximated by a straight line. That is what we said, and that particular straight line is characterized by these two quantities, and they are the strength parameters. So what we get is strength parameters are for this range of stress for the samples tested, strength parameters are phi and c, and this is what we obtained from the series of triaxial tests that we conducted. Okay. So, now we are in a position actually to look at the major features of the stress strain response. What we have seen is that ultimate shear strength of soil and rock increases with the increase of mean normal stress or increase in confinement. That means, if you have got the same type of rock occurring at great depth underneath the ground surface, as well as it has at another level near the ground surface, you have got an identical deposit of rock, then the strength that the deeper element is going to exhibit, the strength behavior that the deeper element is going to be able to exhibit is going to be much larger compared to the strength of the shallower element. Now, as I mentioned when I was talking in the talking about the Morse circles in the previous slide, is that for soils and rock, the increase of ultimate strength, actually there is a mistake here. So, for soils and rock, the increase in the ultimate strength are actually non-linear. So, Mohr Coulomb failure criterion is going to hold only if the range of stress variation for that particular problem is relatively small. And if you have to consider, if you are set with a problem which involves variation of stress, normal stress over a very large range, then you need to consider a curved nonlinear failure envelope. So, what I mean by that is, say you have got tau versus sigma plotted for a series of triaxial tests, and then you might get a failure envelope which is not linear. You can see that this particular failure envelope is convex upward. So, the Morse circles for this particular failure envelope were possibly like this, and you might have another Morse circle on the other side of the axis. So, in this situation, if you have to consider a problem in which the range of stress could vary over a very wide range, then this is the range of stress variation. In that case, you have to consider the nonlinearity in the failure envelope, and there are several types of modifications available over the linear assumption that we indicated in the slides that I discussed little while ago, and you have to consider one of those modifications. And one such modification was the failure criterion given by Hoek and Brown for intact rock particularly. Okay. So, so you have to consider nonlinearity of the failure envelope if need arises. a few more features. Soil and rock are weak in tension, they cannot take tension, and that was clear from the failure envelope that we illustrated in the previous screen there. So this we were considering a nonlinear failure envelope in that case, and what you saw there is that on the tension side, you remember that we were following compression positive convention, and here we have got counterclockwise shear stress positive, and for the normal stress, as I indicated, compression was treated as positive. So what becomes clear is that this value is relatively much smaller compared to the range of compressive stress that a sample can withstand. So this is the tensile strength of the specimen. Okay, so soil and rock are weak in tension. They normally we tend to make a simplifying assumption that they do not have any tensile stress at all. Second aspect is simple shear causes a volume change, and that was evident from the triaxial stress strain data that we schematically presented near the end of the previous lesson. And what you have here, what we were having at that stage was for application of shear stress, we were also having a change of volume, and this type of behavior of shear volume coupling is called dilatancy or contractancy. Normally what you would expect is that when you apply shear stress, then there is no volume change, whereas when you apply normal stress, then only there is a volume change. But in case of granular material, what we tend to see is the feature of dilatancy, where when we apply shear stress, then the volume also tends to change. We are going to look at the details of this type of behavior in the next little bit. And also you should have noticed that the shear strain response, or deviatoric stress versus axial strain response that we illustrated when we were talking about the triaxial tests in the last lesson, was highly nonlinear before failure, before reaching the peak value of the deviator stress. And from the discussion, it is evident actually in this particular case we are taking the peak value of the deviator stress as the condition for failure. Okay. Now we want to illustrate why there is a volume change when we have when we apply a shear stress on a soil or rock specimen. In order to illustrate that, we consider a jointed rock mass shown schematically on the screen there. So if we want to apply shear stress on horizontal planes at the top and at the bottom, then let us try to see what would happen. Okay, you just keep track of what is happening. You will see that in order for the sliding to take place, the rock has to, the top piece of the rock has to climb up in order to climb across the serrations of the joints, and if the normal stress applied during conducting such type of test is large enough, then in fact the joints may shear and break off, as is shown by this particular piece here. And also you would have noticed that the small piece of rock from the corner top right corner of the bottom piece also broke off as this schematic experiment was being conducted. Okay, so another thing I want you to notice here is that there are two arrows, two horizontal arrows shown here, and the bottom arrow in this particular case indicates the bottom of the bottom piece of rock, whereas the top arrow indicates the original, the position of the top piece at the beginning of this schematic experiment. Okay. So let's do this again. Let's continue. Let's take a second look at this particular schematic experiment. So what happens here is that the top piece tries to climb up as it is sheared to the right of this screen, and this involves a change of volume, and you should have also noticed that the void space in between the top piece and the bottom piece increases during this process, and this type of behavior is called dilatancy. Let us consider the reverse of it, and in this case we are going to consider a assembly of spheres. We could have done the same thing using the two pieces of rock which we were considering in the previous example and going in the reverse direction in time, but in order to give you a new flavor, I considered a piece of a block of soil like material composed of uniform spheres. Now let us consider that these spheres are packed in a relatively loose configuration as shown on the screen. Now what we are going to do in this case, we are going to try to keep the bottom of these two layers of spheres at the same location, and we are going to try to shear the top of the specimen to by applying a shear stress to the right of on the horizontal plane to the right of the screen. So just have a look at what happens, how the deformation evolves. So the spheres, they are going to try to climb down and occupy the void space, and in the process what is going to happen is that they are going to sink downward. They are going to sink into the space which was originally void space. So what is happening here is that we are going to end up with an assembly of spheres which are going to be in a state of denser packing compared to the packing that we originally began with. So if you have got a specimen which was originally loose, then if we apply shear stress, then what we are going to have, we are going to reduce the void ratio, and we are going to end up with a state of packing which is a much denser assembly of individual soil or rock fragments, and that is indicated when you compare the top level of these spheres with the original elevation of the top indicated by the arrow at the top of this particular screen. So this is the final elevation of the top, and the arrow noted on the screen indicates the original top elevation. And this much of volume change is because of the contractancy. Okay, let's do it again. Let's have another look at it. So this is how contractancy developed, in this particular case, because we began with an originally loose assembly of spheres. If we were to begin with an originally dense assembly of spheres, then we would have gotten dilatancy as we had in case of the rock specimen, the thought experiment of the rock specimen that I showed a little bit a little while ago. Okay. So now we can talk about the failure criterion in a little bit more detail. That if you consider the simple case of linear failure envelope, and such type of linear failure envelope is called Mohr-Coulomb failure envelope, then you can show that the minor principal stress at failure sigma 3f is equal to the major principal stress at failure sigma 1f multiplied by tan square of 45 degree minus phi by 2 minus 2c tan of 45 degree minus phi by 2. And also you can show that the shear stress at failure represented by the point of tangency of the Mohr circle representing the state of failure and the Mohr-Coulomb failure envelope, at that point, at the point of tangency, tau f is going to be given by sigma f tan phi plus c, where phi is the friction angle as I indicated before, and c is the intercept, cohesion intercept, as shown on the sketch near the bottom right of this particular slide. Now the angle, you should also note that the angle between the major principal stress at failure and the failure plane is always 45 degree minus phi by 2. We are going to prove the first relationship, this one here, in the next little bit. But before I do that, let me explain the second point. So let's find out what is this angle. So this angle here is equal to 90 degree plus phi, and from the discussion that we had on Mohr circles the other day, you can imagine that the angular spacing between the state of stress represented by sigma 1f and the point of tangency is going to be given by half of this included angle, which is 90 degree plus phi. So in this case alpha is equal to 90 degree plus phi, 2 alpha is equal to 90 degree plus phi actually. So that gives us alpha is equal to 45 degree plus phi by 2. Now since sigma 1f, the plane on which sigma 1f is occurring at 90 degree to the direction of sigma 1f, so what we have is the angle between sigma 1f and the plane at which the failure is taking place is going to be given by 45 degree minus phi by 2. In other words, you recall the triaxial sample, and in this case let me open a new page here. So if you have got it, if you recall the triaxial sample that we were testing, sigma 1f was in the vertical direction oriented in this manner, and sigma 3f would have developed in this manner for the triaxial test that I illustrated in the last lesson. In this case, you are going to have failure on a plane which is inclined at 45 degree minus phi by 2 to vertical. Okay, so that's what I mean. So on this particular plane, the relationship between tau f and sigma f. So if you imagine that there is a normal stress on this plane, and let's call this one sigma f, and let's call this one, actually it is going to be the other way around, no, that's all right. Now this is going to be tau f. So then the relationship between tau f and sigma f is going to be tau f is equal to sigma f tan of phi plus c. Okay, so there on this particular failure plane, the value of the shear stress that leads to failure reaches a critical value given by a combination of the normal stress on that particular plane and some material properties, namely the friction angle and the cohesion intercept. This is the failure criterion that you should that is the failure criterion called the Mohr-Coulomb failure criterion. Now let us try to prove the first expression, sigma 3f equal to sigma 1f tan square 45 degree minus phi by 2 minus 2c tan of 45 degree minus phi by 2. Okay. So for doing that, what we do is to check the geometry. So here what we have is sigma f versus tau f, and then let us consider a Mohr circle at failure, and that Mohr circle is going to be tangential to that Mohr circle will be a Mohr-Coulomb failure envelope given by phi and a cohesion intercept c. Now this point here, as you have learnt already, is given by tau f minus sigma f. So the normal stress on that particular plane is sigma f and the shear stress is tau f. Now let us consider the geometry of this situation here. So since the angle that the failure envelope makes with sigma axis is phi, then this distance here is going to be given by this distance here is going to be given by c cot phi plus sigma 1f plus sigma 3f divided by 2. Recall that this value here is sigma 1f and this value here is sigma 3f. And we also know that this particular distance or the radius of the Mohr circle is given by sigma 1f minus sigma 3f over 2. Using these two results, we can write sine of phi prime is going to be given by sigma 1f minus sigma 3f over 2 divided by C cotangent of phi plus sigma 1f plus sigma 3f over 2. Recall, try to remember this this last relationship that we derived here, and I have to erase everything from this particular screen other than that. And recall, actually try to remember the geometry that we were considering as well. Okay. So then what we can collect the terms, and we can go through the geometry, go through the algebra, and we can show that sigma 1f is equal to sigma 3f multiplied by 1 minus sine of phi prime divided by 1 plus sine of phi prime minus 2c cosine of phi prime divided by 1 plus sine of phi prime, and that in turn will give us sigma 3f multiplied by tan square 45 degree minus phi by 2 minus 2c tan of 45 degree minus phi by 2, and this is the relationship that we were trying to derive. Okay. So then there is a definite relationship between sigma 1f, sigma 1, that the major principal stress at failure and the minor principal stress at failure, and the material properties, namely the friction angle and the cohesion intercept. So if you know the values of the friction angle and the cohesion intercept, and also if you know what is the cell pressure or what is the minor principal stress, you could say, you could predict at what major principal stress or what is the value of the axial stress at which the sample is going to fail. Let us take an example on this one. Let us consider a rock sample, consider a case of rock sample, rock specimen for which the UCS is equal to 140 MPa and sigma 1 at failure is 550 MPa in one triaxial test, and sigma 3 at failure in the same triaxial test is 100 MPa. Now our problem is to find phi and c for this particular rock specimen. So how do we proceed? We first take a look at the equation that I derived, and noting that UCS is essentially equal to sigma 1f for a case where sigma 3f or the minor principal stress at failure is equal to 0. So if you note that, then what you could write is C is equal to UCS, unconfined compressive strength, multiplied by tan of 45 degree minus phi by 2 divided by 2, and from that what we get is tan of 45 degree minus phi by 2 is equal to 2c divided by UCS. Remember this relationship and I am going to erase everything on this tablet. Then we make use of the triaxial test data, and let us see what we can come up with. Again we make use of the equation that we derived, substituting for sigma 3f and sigma 1f the minor and major principal stresses at failure. What we see is this. So these two terms, this one here and this one, was as we derived just a few minutes back. Immediately before I erase the tablet, if you recall, and from this what we get is C. When we complete the calculations, then C can be shown to be equal to 34.6 MPa, and when you back substitute this value of C in the original equation, namely sigma 3f equal to sigma 1f multiplied by tan square 45 degree minus 5 by 2 minus 2c tan of 45 degree minus 5 by 2, the equation that we derived earlier. If you substitute that value here, then what you get is phi is equal to 37.4 degrees. So these are the results. Then your C is 34.6 degrees, and phi in this particular case is equal to 37.4 degrees. So here we made use of one unconfined compression test and one triaxial test for getting the strength parameters of interest. Okay. Now we introduce the concept of effective stress. For saturated soils and rock mass, effective stress is given by this expression here, sigma prime equal to sigma minus u multiplied by 1 minus as plus a minus r. Now what are these terms is going to be, let me explain that before I proceed any further. Let's say you have got an element of soil which is composed of several different grains. And what we have, it's a saturated sample, and the pore space is full of water in this case. So then we take a cut across the sample, and if you look at the plan view of this particular cut, then what you might see is that a portion is going to be showing soil grains, whereas in other areas what you are going to have is water. So these are soil grains. So let us give a name to the section. So this is section AA. So these are soil grains, and in between is water. And these are also soil grains. So then now what we have is that if you consider that this particular element is subjected to a compressive stress in that direction, then a part of it, a part of the compressive stress is going to be transferred through intergranular contact, through the intergranular contact between individual soil grains, and part of it is going to be taken by pore water. Since the intergranular contact is of a very small proportion in comparison with the pore space, with the area under water, then what we could write is that, actually let me write that one. So sigma prime, let's say sigma is going, a part of it is going to be borne by intergranular contact stresses, and part of it is going to be borne by the pore water pressure, and this quantity A subscript S is the amount of area at which the individual soil grains are in mutual contact, and U is the pressure that is borne by pore water, or that is called the pore water pressure, and on top of it you could have some electrostatic forces of attraction and electrostatic forces of repulsion, and that is particularly true in case of soils composed of charged particles such as clayey soils. Okay, so that is the expression there, and since A subscript S is usually very small, and that is particularly true if you have got very strong soil grains, incompressible soil grains, in comparison with 1 is very small in comparison, AS is very small in comparison with 1, and forces of attraction and repulsion, they balance out. What we could write is sigma prime is equal to sigma minus U, or the effective stress is equal to the total stress minus the pore water pressure. This simple expression works very well for soil and rock if the pore space is interconnected, saturated soil and rock if the pore space is interconnected, and if the pore water pressure, if the pore water or the groundwater within the mass of soil or rock is not in relative motion in comparison with the solid skeleton. So this is called the so in simple cases what we are going to do, we are going to get the total stress, and we are going to simply subtract from the total stress the pore water pressure, and then we are going to get the effective stress. Okay. Now we look at the effective stress principle. Applied stress on a skeleton of soil or rock, saturated skeleton of soil and rock, is supported by stress at intergranular contacts and pore water pressure, as we have seen already. Now since pore fluid is weak in shear, if we apply shear stress to the specimen, then it can only be supported because of effective stress. So soil behavior in shear stress shear strain response is controlled by effective stress rather than the total stress, and this is the effective stress principle introduced by Carl Terzaghi in early 1900s, which led to the development of the science of soil mechanics and geotechnical engineering. It's a very important principle, actually seminal in fact, that led to the entire development of this field of learning. Then factors affecting shear strength. What are the factors that affect shear strength parameters? Number 1 is effective stress. So higher the effective stress, as we have noted, that the shear stress that the assembly can support is also going to increase. Second thing is inherent anisotropy, and that is because presence of joint sets or presence of lamination within the mass of rock or soil, that is because of the depositional environment or because of mineralogical characteristics of the solid. Then the third thing that affects shear strength is interlocking. As we have seen that more compact the structure, greater will be the interlock, there will be dilatancy, and what we are going to get is a larger strength in comparison with a comparatively looser assembly. And that is illustrated when we consider typical deviatoric stress versus epsilon axial plot and volumetric strain versus epsilon axial plot obtained from triaxial tests for a loose or soft deposit and dense or stiff deposit, as we see on the schematic plot on the right of this particular slide. Here, as is evident, in case of dense sample, the strength is much larger in comparison with the strength of loose sample, and that is because of the dilatancy really, which is illustrated with the volumetric strain versus axial strain plot near the bottom of these two plots. As we have noticed earlier, loose or soft deposits will contract under shear, and dense or stiff deposits tend to first contract when the axial strain is relatively very small, and finally the sample starts to dilate, as is shown on the plot there. Other factors that affect shear strength characteristics: presence of pore fluid. Some of the rocks exhibit smaller strength under moist or wet conditions in comparison with a dry condition. Then loading rate: if you have got a faster loading rate, generally for rocks and clays shear strength becomes greater. Then if you have got weathered rock or soils, weathered rock sample, then you are going to expect a smaller strength. If you have got a larger RMR, rock mass rating, then you would expect a greater strength of the rock mass. Summarize this particular lesson as well as the last one. We looked at the characteristics of stress strain behavior of soil and rock, looked at triaxial testing and how we can assess the shear stress strain behavior of soil and rock, then how we can obtain Mohr Coulomb failure parameters associated with Mohr Coulomb failure criteria from conducting triaxial tests, and we looked at a list of major factors that affect shear strength of soil and rock mass. And finally, we want to wrap up this particular lesson with a question set. Try to answer these questions at your leisure. The first question that I ask is, give an example of a plane strain and a plane actually the first one should be plane stress. There is a mistake there. So give an example of a plane stress and a plane strain problem. And then second one is really a numerical problem. It involves an 8-meter high excavation for a hill road construction through a 45-degree sandstone hill slope. Within this rock mass there is a single joint with 3-meter spacing and 35-degree dip angle striking parallel to the road cut. The joint properties are given there: phi equal to 45 degree and c equal to 0. The sandstone is dry with a unit weight of 20. Would the cut be safe? So you have to actually look at the cross section in this particular case. So what I say here is really you have got a hill slope. You have got a hill slope which is inclined at 45 degree to horizontal, and you want to cut an 8 meter high slope. So this height here is 8 meter, and there is a joint set within this particular rock mass dipping at 35 degree angle. So this angle here is 35 degree, and the spacing of these joints is also given. So you are supposed to tell me whether this particular cut is going to remain stable during construction or during the operation of the highway. That is the problem there. So with that, I am going to stop this lesson, and you try to answer these questions at your leisure. I will give you my answers when we meet for the next lesson. Thank you very much. Hello everyone, and welcome back. Today we are going to talk about in situ state of stress, but before we carry on with today's lesson, we are going to look at the questions that I gave you as part of the previous lesson. So these are the questions. The first question that I asked was, give an example of a plane stress and a plane strain problem. Now plane stress, if you recall, in plane stress problem, what you have are essentially two principal stresses in one plane, and the out of plane principal stress in that case is 0. So we can consider an example from the perspective of engineering. Wrap up this particular question, lesson. I give you a question set. Try to answer these questions at your convenience. The first question is, a closely spaced family of thrust faults runs parallel to the Himalayas. What is the direction of major principal stress along the thrust faults? Then the second question is, would you expect a sample of gneiss to be stronger in the direction parallel to the bedding or perpendicular to the bedding planes? Third question is, explain why folding becomes more prevalent with depth compared to faulting. Try to answer these questions in your time, and I am going to give you my answers when I meet you with the next lesson. Until then, bye for now.